So far we have learned how to identify proper axis of rotation and symmetry planes as the symmetry elements in different type of molecules. So in this tutorial I'll show you how to work out different, or how to identify and locate different symmetry elements, only including symmetry planes and proper axis of rotation. So let us start with today's tutorial. So let's look at this molecule, which is the very simple molecule which we have been looking at, which is ammonia, right? So you have NH3, right? So this particular proton and nitrogen are in plane. This proton is coming out of the plane of the board, and this proton is going behind the plane of the board. So now if I see what different types of proper axis of rotations are present, I can also draw this as, if I'm looking from the top, it looks something like this. So that helps me identify that there is a, so here I'm looking from the top. So now if you see that there is a proper axis of rotation with C3 order, right, with n equal to 3, which is actually perpendicular to, let me choose a different color, so which is perpendicular to the plane of the board if I look from the top, or otherwise you can say that this is my C3 axis. Okay, so this is, I can write this as C3. So in other words, either way we should be able to identify, and this is the only proper axis of rotation which is present in this molecule. Okay, so the operations, corresponding operations will be C3 to the power 1, C3 to the power 2, and C3 to the power 3, right? So this comes out of C3. Okay, so now C3 to the power 1 is an independent operation, C3 to the power 2 is an independent operation, but C3 to the power 3 is actually equivalent to E. So why we say that? So this is very easy to see. If we do C3 on this, let's do C3 onto this, what do we get? And all the rotations will be anti-clockwise. So you have N, H, you do get equivalent configuration, but the numbers are going to be shifted now. So 1 moves to this position, 2 moves to this position, 3 moves to this position. So this is C3 to the power 1. Now I do C3 again. So I can say that this operation will be C3 to the power 2, right? So again I will get H, and now 1 moves here, 2 moves here, 3 moves here, right? So this is C3 square, which is, so if I call this molecule as 1, this conformation or configuration as 2, this configuration as 3. So 1, 2 and 3 are equivalent configuration, not identical. So if I do C3 one more time, what do I get? I get 1 here, 2 here, and 3 here, right? Now if I do this, this will be my C3 cube operation. So this is C31, C31 on this, C31 on this, 2 times C3 done, so this will be called as C3 square, 3 times C3 done, so this will be called as C3 cube. Now if you notice this one has same orientation of hydrogens as in this one. So I would call this as identical configuration. Okay, these two are equivalent to 1, whereas this one is identical to 1. So then I say that because this is an identical configuration, this particular, or let me call it as fourth. Okay, So fourth is an identical configuration to 1. So I would say that C3 cube is actually equivalent to doing nothing, that is doing identity operation. So in this case, if we list down the operations from C3, this will be C3 and C3 square, which are independent operations, and C3 cube will not be an independent operation, it will be equal to identity. Okay, now let's go to a little more complex molecule where we have more okay, before we actually do that, let's also see what are the symmetry planes present in this. Okay, so let's draw this molecule again the same fashion. So 1 2 3. Now if you notice that there is a plane which contains this nitrogen and hydrogen, and this will be bisecting the angle which is H2 H3, right? So I would draw this as plane of the board and call it as sigma V1. Okay, now if I'm looking at the molecule from top, I can say I can draw it like this. It is very important to understand it correctly. So this is 1 2 and 3, and now my plane is the one which is, now I'm looking from the top, so my plane would appear as a line to me. This plane, if I'm looking from the top, this view, then my plane would appear as a line to me. And now this plane would contain NH1 and will bisect this angle H2NH3, right? So this will be called as sigma V1. Similarly, there will be a sigma V2. So sigma V1, sigma V2, sigma V3, right? These are the symmetry elements or symmetry planes present in ammonia. Okay, now let us move to more complex molecules and look at proper axis of rotation and planes. So again, we have discussed this case, but let's discuss in more detail so that it is very, very clear. So 1 2 3 4. Okay, so now what are the symmetry, what are the proper axis of rotations present? So proper axis of rotations, there will be one C3. How many C3s will be present? So let's try to draw it. So if I try to see that there is a C3 axis passing through CH4, which results into rotation of H1, H2 and H3. So this is collinear with CH4 and rotates H1, H2, H3, right? So let's call this as one C3 axis. So this is my C3 axis. Similarly, I can have a C3 which is passing through CH1. So I will say that there is another C3 which is collinear with now CH1 bond. And now this will rotate the rest of the three hydrogens, which is H2, H3 and H4. So this should be very easy to see now, right? This is my second C3 and this will be rotating anti-clockwise like this. So H2, H3 and H4 will be rotated now. There will be another C3 which will be passing through CH2 and rotates H1, H3, H4. Similarly, the last one will be collinear with CH3 and it will rotate H1, H2, H4. So this is there should not be any problem in now locating the C3 axis. So there should be 4 C3 axes, independent 4 C3 axes. Now each of the C3 will give rise to C3 and C3 square operation. We have seen that in case of ammonia. So this will lead to operations. If we list down the operations due to C3, there will be 8 C3 operations, because each of this there will be 4 C3 1 operations and 4 C3 square operations. Remember that C3 cube operations will be equal to identity, so that will not be counted. So you will have 4 C3 elements and 8 C3 operations. Okay, so now let us look at, is there any other proper axis of rotation in this? So let us see what all we have. So there is one C2 axis. I mean, not one, there are 3 C2 axes, but let us see how do we identify or how do we locate C2 axis in this one. To be able to locate C2 axis in this one, it will be easier if we draw the molecule like inside the cube. So let's draw this molecule inside the cube. Excuse me for the bad drawing of cube. So now in the center of this cube, where the 4 diagonals will meet, this will be the carbon atom. Okay, and my 4 hydrogens will be oriented along the, so from carbon to hydrogen like this, and there will be 2 hydrogens which will be meeting with these 2 vertices. So now I should be able to identify the C2 axis. So C2 axis will be present perpendicular to this top face of the cube like this. Okay, this will be going, if I'm going through carbon, so let me draw it correctly. So this will be something like this and passing through this. So now this is actually bisecting which angle? So if I label this as 1, 2, 3 and 4, so this C2 is bisecting H1 C H2 angle, and simultaneously it will also be bisecting H3 C H4 angle. Okay, so this is one C2 axis. Now let's see if we have any other C2. So if we carefully see that there is this particular face, so there is one C2 which is going through this face, so the horizontal face. This is my C2. Now this will be bisecting H2 C H3 angle, and on the other side this will be also bisecting H1 C H4 angle. Now there would be one C2 which is going from the front plane, center of the front plane to the center of the back plane, passing through carbon atom. So that will be bisecting H2 C H4 angle and H1 C H3 angle. Now if you carefully notice that all 6 carbon hydrogen angles has been listed here, so that means there is no other possibility of listing another C2. So that would mean that there would be 3 C2 axes, and each C2 gives rise to one C2 operation, so there would be 3 C2 operations. So if we say that the operations, it will be 3 C2 operations. Elements, it will be 3 C2 elements and 3 C2 operations. So this tells you how your C2 proper axis of rotation will be oriented, right? Okay. Now let's look at the planes in this particular molecule, where the planes will be and how many planes will be there. So now if we try to list down the planes, we will see that there will be plane containing H1, C, H4 and bisecting the angle between H2, C, H3, right? So there would be a plane which will contain H1, C, H4, this one, and it will bisect this angle. Okay. So now if it has to contain one particular angle and bisect the other angle, and there are 6 such angles, that means there can be 6 such planes. Okay. It will contain one of the angle and it will bisect the opposite. Okay. So for example, if I'm saying that it is containing H1C H4, this one over here. So if I'm saying that it is containing H1C H4 angle over here and it is bisecting H2 HC3, then I can say that there would be one plane which will be actually containing this and bisecting this, right? So vice versa it will be. So let me mention that. So this, the second plane will be containing H2C H3 angle and bisecting H1C H4 angle, right? So same way, if we list down all 6 angles, there would be 6 sigmas present, and these will be called as dihedral planes because these are bisecting the angles. So 6 sigma D's will be present in this molecule. So we are only listing down the symmetry planes and proper axis of rotation in different molecules. So this is for tetrahedral molecule. Now let us go to even complex molecule, which is octahedral molecule, because there are the number of elements and operations are huge in that case. So let us list it down. Let's first draw the molecule. So let's see, let's draw a generic molecule. Now all 6 bonds in this case are equal because this is an octahedral molecule, right? Okay. And then how do we get a sense of where it is? So let's draw a plane around these 4 B atoms so that we know that these 5 atoms are forming one plane, and then this particular atom B and this B is actually coming out of the plane and this is going below the plane. So let's say if I'm drawing it like this, it looks like this. Okay. So in other words, if I try to draw it in a 3D projection, it looks something like this. Okay. So you have at the center is A, and then you have 4 B atoms. This is another way to draw. So drawing is very, very important because you need to understand the 3D conformation of the molecule. Otherwise, you will not be able to draw the or write down the symmetry elements or symmetry operations present in this. So let me also list down. Now another way to look at this molecule is, which is very interesting. So if I'm looking from this side, okay, so just see that this B5, so if I connect B5, B3 and B2, it forms the face of an equilateral triangle. Okay, similarly B1, B4, B6 also forms the face of an equilateral triangle. So if we look via equilateral triangles, keeping equilateral triangles on the front face, then how the molecule looks like, it will be interesting to see that These are the equilateral triangles that we have drawn. Okay, now this one is at the top because from we are looking from this side. So you have B5, B3 and B2, and the one which is here is actually, it looks like a star if you now see. And the bottom is B6, B4, and this side is B1. And the center of these two triangles will be atom A, right? So now it will be very, very easy to identify C3 axis of rotation. So now if you see that there is a C3 axis which is passing through the center of these triangles, these two triangles, okay, formed by B2, B3, B5 and B1, B4, B6, right? So that way we can say that there is one C3 axis. Similarly, how many, now if we try to identify how many C3 axes are present, so that will depend on how many equilateral triangles can we make out of this. So similar to B5, B3, B2 and B1, B4, B6, we can also make with B5, B2, B6, right? B5, B2, B6, and look from the other side, this side. No, sorry, not B5, B2, B6. Yeah, B6, we can make it as B2, B3, B6. Okay, the adjacent side and this one. Okay, so if we let us try to count how many C3 axes will be present. So there will be 4 such C3 axes. So let us try to list them down. So let's try to list the faces of the triangle that are formed by B atoms. Okay, so one is B2, B3, B5 and B1, B4, B6. What are the other triangles which can be formed here? So the other triangle is B2, B3, B6. Okay, instead of top, we can now go to the bottom, and the second face thus will be B1, B4, B5. B1, B4, B5. Okay, so these are the two this side. Now similarly we can go from this side. Okay, now that will be B1, B2, B6, and the corresponding at the back will be B4, B5, B3. Okay, now also B1, B2 will be forming another triangle with B5. So B1, B2, B5 and B1, B2, B5 and B3, B4, B6. B3, B4, B6. So these are the 4 C3 axes which will be present. Can we see, did we miss any other axis? I guess no, because we have covered all possible combinations. So 4 C3 axes, and thus operations will be, number of operations will be 8 operations. Remember, each C3 will give you 2 operations. So 4 C3 axis will give you 8 C3 operations, right? So that is for C3. Now let's see what else does it have. Let's draw this molecule again. Now there would be a C4 axis. So C4 axis will be oriented along opposite BAB. So that is the BAB which is making 180-degree angle. How many such BABs are there? There are 3 such BABs. Right. So let's keep the same nomenclature. 1, 2, 3, 4, 5, 6. Okay. So we have 1, 2, 3, 4, 5, 6. So this is the one which is collinear with B5, A, B6. Okay. Then we have collinear with B4, A, B2, and there is one which is collinear with B1, A, B3. So there are only 3 such options because there are only 3 such bond pairs which have 180-degree angle. Others will have lesser angle, so that will not be a C4 axis. So now if you do a C4 operation, it will be like this, right? So this is my C4 axis. So B1 will be replaced with B2 and so on. Similarly, if I'm doing C4 operation along this axis, the rotation will be between B4, B5, B2 and B6, right? So this will be forming as a plane. And this will be my rotation, C4 rotation. Okay. Now, same way, collinear with C4, there will be 3 C2 axes present. Now each C4 will give you how many operations? 2 operations. So C4 will give you 6 C4 operations. Okay. And well, this will actually give you, because C4 will be 1 operation, C4 square will be equivalent to C2, which is listed this one because this is the collinear axis. Then you have C4 to the power 3 as an independent operation. C4 to the power 4 will be equivalent to identity operation. So each C4 will give you 6 operations, 6 C4 operations, and collinear with C4 there will be 3 C2 axes, which will give you 3 C2 operations. Now what else? Any other proper axis of rotation? Yes, there are 6 more C2s. What are those C2s? Any ideas? So let me draw this molecule again because otherwise it will be difficult to annotate. So now there will be 6 C2 which are perpendicular to the 180-degree angles formed by these C4s. So B5, A, B6. Okay, now this perpendicular can be in 2 directions. So you have basically what you have is this axis and this axis, right? So you have axis going through like this will be C2. Similarly, so each of this will have 2 perpendiculars. So all of this will be perpendicular to these 3. So B4 next will be B4, A, B2, and third will be B1, A, B3. So perpendicular to B1, A, B3 will be passing through. So if I'm drawing a line like this, so it will be perpendicular to this one, right? So 6 C2s will be present. So now let's also list down the symmetry planes. How many symmetry planes will be present in this one? So planes are simple to see. The planes which are actually planes containing the 4b atoms and the central atom. For example, you have B1, B2, B3, B4. This plane will be called as sigma H. Similarly, you have B1, B6, B3, B5, B1, B6, B3, B5, and third one will be B2, B5, B4, B6. These are the planes containing 4b atoms, and of course the central atom will always be there. And these are three such sigmas. So 3 sigma H. Then planes, there will be planes containing 6 C2s perpendicular to C4s. Okay. Now these are the 6 C2s present. So for example, this C2, so there will be a plane containing this C2 and a plane containing this C2. Okay. So basically the planes which are dividing these planes. So this particular plane can be divided in two ways. So one way is marked in red over here and another way is marked in red over here. Similarly, these 4 planes can be also divided by two possible ways and two possible ways. So there will be 6 such planes which are called as 6 sigma Ds. Okay. So I hope that these 3 molecules should be sufficient, will give you enough understanding on how to locate different proper axis of rotation and planes. So if there are any troubles, we can again discuss during the interaction session. But the idea here is that if you list down all the atoms containing different symmetry elements, so you won't get lost and you will be able to list the exact number of symmetry elements present. Otherwise, if you just keep on imagining and write in air, then it would not take you anywhere. So it's better to list down all the atom numbers which are contained by a particular symmetry element and then try to find out how many such combinations are possible, and accordingly write down all the symmetry elements and operations. Okay, thank you very much. This is all for today.